Okay, so we are going to go over a few recitation problems on induction. So the recitation worksheet and handwritten solutions are posted up on Moodle. I'm mostly intending this if you want a more interactive way to see the solutions to the recitation problems. So I'll go through them in the order that they're posted. So I have a magnetic field is coming through a loop of wire. So the X's here are the magnetic field. So these are pointing into the page. And we're going to say that the magnitude of the magnetic field is increasing, and we want to figure out the direction of the current in the loop. So I have Lenz's law written out by hand up here. This is actually sort of posted in with the solutions as well, but it's also no different than the part that is in the PowerPoint slides as well. There's some problem solving steps for how to use Lenz's law in the PowerPoint slides that you're welcome to use as well. So any of them should be fine. And so the first step in Lenz's law is to figure out what direction is BEXT, the external magnetic field. So the external magnetic field is the magnetic field that exists in the beginning, okay? It's the background, and these are the X's. So here for step one, I'll say BXT is into the page. And often you need to use the right-hand rule for this, but we don't here. We were just told what the magnetic field was. And then we're going to figure out, is the flux increasing or decreasing? Okay, so flux is B a cosine of theta. So right, flux can either change because B changes, or it can change because A changes, like if the loop gets bigger or smaller, or the flux can change if something is rotating as well. And I didn't even write that down here, but that happens from time to time as well. We are told that B, the magnetic field, is getting stronger, which means if B is going up, then the flux is going up. So I will say that the flux is increasing in strength. Now we'll move down to the third. If the flux is increasing, and that's where we are, then B induced and B external point in opposite directions. So this is the step that is Lenz's law that says that the magnitude of the induced magnetic field will oppose the change. So we see that these two are opposite to each other. So that must mean that B induced is into the page, right? If external was out, I said that's backwards. B induced is out of the page because B external is into the page. And now we will use the right-hand rule to determine the direction of the induced current. And I managed to not come home with much of a loop for this, so we'll just have to make do with this loop of wire that I have here. So if I want B induced to be out of the page, I'm going to make my fingers go out of the page in the middle of the loop, and my thumb wraps around this way. So that is in a counterclockwise direction. So we'll say that I induced is that way, which is counterclockwise. Okay, let's move on to the next one. So immediately after the switch is closed, what is the direction of the induced current in the upper lip? And we're going to give a direction as though we are an observer looking down on the lip on the loop. So I'm going to put a little eyeball up here, right? So there's my eyeball. It's looking down. So we want to sort of decide how it is if we are up above the loop looking down. Okay, so we'll follow our Lenz's law. We need to figure out the direction of the external magnetic field. Okay, so this is the loop that is going to have induction go on with it. So this loop down here must be the loop that is causing the external magnetic field. Okay, so we need to actually do a little bit of thinking before we're ready for step one, which is to figure out the direction of IEXT, the current in the external current. So the long wire on the long line on a battery is the positive terminal of the battery, and current always comes out of the positive terminal of the battery. So once this switch here is closed, current will be going around in a direction like this. And so as we are, if we are an observer looking down on this loop, we see it going around in this direction. That is the counterclockwise direction, okay? So I'm going to put a little step 0 here and say that IEXT is counterclockwise. And now we're ready for step 1. the direction of BEXT. So now let's make our loop. Right, and our loop, I'll try to kind of match what it looks like on the thing. So I know that current is going around like this. And so I will put my thumb like that in the direction of current. And in the middle of the loop, that is going up. My palms are looping up. So this field is coming out of the page here, back down, or sorry, up here, and then down outside. So we're interested in what's going on in the middle of the loop because that is where the magnetic field is the strongest. So we will say that BXT is up. Actually, rather than drawing an arrow up, because that kind of makes it seem like it's increasing in strength, I'm going to say up. So what that looks like here is that here's my BEXT lens. Okay, and of course, also the magnetic field isn't just pointing up, right? It's going in these circles that look like this. But for induction, we're interested in the magnetic flux that actually goes through this loop. So we only care about the magnetic field here. So there's my BEXT. So, and now we're going to say what the third step here is what's happening to the flux. Or sorry, the second step is the flux increasing or decreasing. So as we close the switch, the flux goes from nothing through this loop because there was no current in this loop when the switch is open. And as you close the switch, now there is current through this loop. Okay, so the flux is going to go from nothing up to something. So that must be an increase in flux. So our third step is we're again going to follow that the flux is increasing, so B induced and B external must point opposite to each other. So I'll go ahead and draw that BEXT has to point down. Excuse me, that's not BEXT, that's B induced. So the external field points up, so the B induced, which I'm trying to do in blue, points down. So B induced is down. Okay, and now we're going to use our right hand rules to try to find how we get it to point down in the middle of the page. So I want down, my fingers are going to go down in the middle of the loop, and the way that my thumb wraps is clockwise. So the current is going around in this direction because my thumb points in the clockwise direction. So I'll draw that here, like that. So I induced looks like that. And I kind of skipped my rules, but I'm about to do the fourth rule, which is use the right hand rule to figure out the direction of I induced. And we just did that. So I induced is clockwise. I realize that I'm sort of mostly doing things that involve the flux going up, and I don't want you to think that it's always that way. So let's just consider the opposite. So pretend like the switch is closed and then it opens. If the switch was closed and then it opened, then we'd be the same here, right? The external current is still counterclockwise and B external would still be up. But if the flux is decreasing, if the flux was decreasing, then we would come down here to say that if the flux is decreasing, then B induced and B external point in the same direction. So we would have B induced is up. Okay, so the Lenz's law says that the induced current and field will oppose the change. So because the flux is weakening, nature wants to reinforce what it used to be like. So that would make the magnetic field, instead of these down arrows, that would make it point up, as I said here. And if you want to get the magnetic field to point up, then you take your loop of wire and you do magnetic field is up, your thumb points in the direction like that, and the magnetic field is coming up, and that must mean that it's going around in this counterclockwise direction. And that would be CC-wise. So just a little bit of a different version of the same question. Okay, let's move on to a transformer question or two. So this right here is going to be a step up transformer. Okay, so it's a step up transformer because there's more loops on the secondary than there is in the primary. So the first coil we always call the primary, and since that's what's plugged into the wall here, that will be our primary coil. So we go primary to secondary, and then actually these loops are connecting to another transformer, which is going from primary to secondary. This here is a step up transformer, so it will step up voltage. And that must mean that it steps down the current. Okay, so a step up transformer always steps up the voltage. And this is going from 1, 2, 3, 4 loops down to 2 loops. So this is a step down transformer. So it steps down and it steps up the current. Okay, a steps up voltage, we can use equations for this, but just as easy is just if it doubles the number of loops, it doubles the voltage. Okay, so there's 120 volts here, and we will double the number of loops, so we'll double the current, double the voltage. So this is 120 volts, which must mean that I have 240 volts here. If there's 240 volts in this whole loop, there's 240 volts on both of these. And then we're going to step it back down to 2 loops. So this ends up back down to 120 volts. So we've stepped it up, then we've stepped it back down, and done it that way. Okay, so you can also use the equation sheet version of this, which will give you the same answer. So pull up the way that it's written on the equation sheet. So it says Vs over Vp, so that's V secondary over V primary equals Ns over Np. Right, so if secondary, if we look over here, Ns over Np, secondary has 4 loops, primary has 2 loops, then we know that Vs over Vp has to equal 4 over 2. So I'll say that Vs over Vp equals 2. All right, so the voltage on the secondary has to be twice as big as the voltage on the primary. And you can do that. So I guess, yeah, if V primary is 120 volts, then we can say that Vs is 2 times 120, and that's 240. Okay, on the next problem, we have been given this intermediate current, and we've said that it's 1 amp. So this is a whole long loop, so there's 1 amp of current everywhere in this wire, and I want to figure out what is the current through the light bulb. We actually don't even care what's going on over here. I guess we do need it. I take that back. We do need it because we need to know that actually there's delta V as the drop across this loop is 240 volts. And we know that from this previous problem, right? We already figured that out, that there was 240 volts in the intermediate loop. Okay, so we have 1 amp of current and 240 volts. And then delta V on this is 120 volts. And now just using this sort of, it steps down the voltage, which must mean that it steps up the current. So the number of loops has gone down by a factor of 2, which must mean that the current has gone up by a factor of 2. So I'm going to go ahead and circle 2 amps without using an equation, just by using the fact that I know that the number of loops has halved, so the current must double. But using the equation sheet, you could also look at IS over IP equals NP over NS. And now you see that this form of the equation, these two equations have a very similar form, right? S over P and S over P. But this is an S over a P, so a secondary over a primary, and this is a primary over a secondary. So we will say that solve that for I of the secondary is NP over NS times IP. So I've just multiplied times IP on both sides of the equation, like that. So these IPs will cancel, and we'll solve for that. Number of loops on the primary is 4. Number of loops on the secondary is 2. And current in the primary is 1 amp, because this right here is the primary. So don't let this confuse you, right? 1 amp of current is going through the secondary of this transformer over here, but it's also going through the primary of this transformer over here. So 4 over 2 times 1 is 2. For our the next problem, we're going to connect a 6-volt battery to one side of the transformer. I have coil A over here, so that's the primary, and point B over here is the secondary, and we want to figure out what happens to the voltage. So this is a step-up transformer, so it should step up the voltage, which would mean that we double the voltage as we step up as we double the number of loops. But actually, this is a bit of a trick question as a prep for when things like that show up. Right, this is a battery. Right, it says right here that it is a 6-volt battery. So the thing about a battery is that it is DC. Right, it is direct, unchanging current. Transformers operate on the principle of induction. The reason that there is a current on this loop is because a current is induced in this loop due to a changing current in this loop. So we didn't have to deal with that here because what was plugged in here was 120 volts to a wall outlet, and we get AC electricity out of our wall outlet. So this was a normal way that a transformer would act. But if it's just connecting to a battery and it's a steady current through here that's not changing, there will be no induced current or EMF in the secondary of this transformer. It will just read 0 volts. Okay, and last but certainly not least is one long Faraday and Lenz's law problem. So I have a triangular loop of wire that has a resistance of 0.3 ohms. It's in a uniform magnetic field, which means this uniform magnetic field is pointing into the page. But the field strength is going to change from 0.3 Teslas to 0.1 Tesla in 50 milliseconds. Okay, we want to figure out the magnitude of the induced EMF in the loop. We'll figure out the direction. So the magnitude of the induced EMF, that is a Faraday's law question. Faraday's law will tell us that. The magnitude of the induced current, the direction of the induced current, that is a Lenz's law question. We'll use those 4 steps that we used on the previous page. And then we'll figure out what is the magnitude of the induced current in the loop. Okay. So to figure out the induced EMF in the chapter 21 problems, there's only 2 equations that have anything to do with an EMF. One of them is this one, that is BLV, and the other one is this one, which is the EMF is number of loops times change in flux over change in time, like that. This is the formula for motional EMF. This is like a loop that is traveling through a magnetic field. So this is not the right one. We also don't have a velocity, so that could be another clue that this one is probably not gonna work out for us. We will use this one. Okay, so we have one loop. This isn't a solenoid with many loops, so we'll just get rid of that N. And we are looking for the magnitude of the induced EMF is the absolute value of the change in flux divided by the change in time. Okay, so let's go see what we have up here. I've been told a resistance. It's not yet clear to me how that is going to play a role in here, because I know that the flux is B times A times cosine of theta. And we weren't told anything about angles. So it's probably reasonable to assume that we can just assume that cosine of theta is 1. And that is true. So right, so if you want to think about theta as being the angle between the magnetic field lines and this angle here that points perpendicular out from the loop, that's how we defined theta, right? Both of them point straight in and out of the page, so that theta equals 0. And just to prove that it's true, find a way that you can see this. Somewhere it usually works. Okay, well, I just plugged in cosine of theta into my calculator and it equals cosine of 0 into my calculator and it equals 1. So you can give that a try if you want. So I will just ignore that cosine of theta term and say that it is B times A. Okay, so let me rewrite this formula as the EMF. I'm going to ignore this absolute value for now. I'll just remember at the end that if I get a negative number, I'll ignore a negative number. That's all the absolute value means. Is the triangle always is the final minus initial over delta t. And let's plug in BA here. So I will say B final, A final minus B initial, A initial divided by delta t. So that's the formula that is sort of an expanded version of what we were looking for. Okay, so the field strength changes from 0.3 to 0.1 Tesla in 50 milliseconds. So let's plug in our 50 milliseconds for the time. So that is 50 times 10 to the negative third seconds. Milli is negative third. The field changes. So I got two field strengths. There's an initial and a final field strength. I also need an A. That's the area of the loop. We should probably calculate that. This is a triangle. So the area of any triangle is always 1/2 base times height. 1/2 times base times height. So that is 1/2 times base is 0.2 meters times height is 0.2 meters. And calculate that. I got 0.02. Okay, so we'll just plug in these numbers. Oh, that's not 0.2 meters, but 0.2 meters squared. It's an area, so that should have a length squared. So B final is 0.1, right? That's the initial. It changes from that to that. So we'll go 0.1 Tesla times 0.02 meters squared minus 0.3 Teslas times 0.02 meters squared. And plug all of those things into our calculator. 0.02. And I have 0.08 volts that I have when I plug all of those things in. And I actually got a negative number here, but I took the absolute value. So I could put my absolute values all along here if I wanted. So it's 0.08 volts. Let's come up here and take a look at sig figs. So I have 2 sig figs in this one, 2 in this one, 2 in this one. I've only written 1 in this one, so I guess we'll follow the letter of the law and just keep it at 1 sig fig. I think in my posted solutions, I assumed that there was a decimal place here, and this was all 2 sig figs. So if I wanted to write that, that's the 1 sig fig version. If I wanted to write that as 2 sig figs, I'd write it as 0.080 volts. Right? These zeros here are just placeholders. But this one being here actually tells me that it's a significant digit. So for B, what's the direction of the induced current? Now we're going to use Lenz's law. So let's come over here to use the rules for Lenz's law. So we'll say that the direction of BEXT is into the page, and the flux is going down. It's decreasing. So flux is decreasing. And that means that if flux is decreasing, then B induced and B external point in the same direction. So, oops, you can't see that. So the flux is decreasing, so the induced and the external point in the same direction. So that must mean that B induced is also an X because BEXT is an X. And we'll do our last step, which is that we'll use the right-hand rule to figure out the direction of the induced current. And now don't let it bother you that this is a triangle. It is a triangle-shaped loop where you would like your fingers to point into the page. So I'm going to put my fingers pointing into the page on my triangle-shaped loop. And there I go. And my fingers are into the page in the middle, and my hand is rotating around clockwise like that. So I induced is around clockwise like that. And last but not least is we want to figure out the magnitude of the induced current in the loop. I know the EMF, that is a voltage, and I know the resistance in the wire. That is 0.3 ohms. So V equals IR, Ohm's law works here. So for part C, we'll say that the EMF is I induced times R from Ohm's law, and we'll just solve for I and get that I is E over R, which is 0.08 divided by 0.3. And 0.08 divided by 0.3 is 0.2667. So depending on whether I wanted to write this as 1 sig fig or 2 sig figs, I'd write it as either 0.3 amps if I want it to be 1 sig fig, or I'd write it as 0.27 amps if I want it to be 2 sig figs. Just like that. All right, and that will close off this video. So I'll see you next time.